Hello everyone. So today I'll be solving this building teams problem from CSES. So the question says that we have some n pupils and we have m friendships between them, and we have to divide the pupils into two teams in such a way that no two pupils in a team are friends. Okay. Now here the friendship is basically edges. Okay. So edges are friendships here. Okay. And we have to output for each pupil whether they are belonging to team 1 or 2, and if there is a valid arrangement possible, we have to print it. And if it is not possible to assign each pupil to individual teams, like into one of the two teams, then I have to print impossible. Okay, let's look at the input. So here we have 5 nodes, and these are the connections like friendships. So I have one here. One is a friendship, like has a friendship with 2. Then one also has a friendship with 3. Okay. Then I have 4 and 5. Okay. So here, how can I divide them into teams? Okay. Let's say I start with 1. Okay. So let's assign 1 to team 1. Okay. Then I cannot put 2 in the same team as 1. So I have to put him inside another team. So let's make it 2. Okay. Then for 3, same story goes, like I cannot put 3 in the same team as 1, so I have to put them in some different team. So 2 again. Okay. Then I have 4 and 5. So either I can put 4 into team 1 or 2, or vice versa with 5. So let's say 4 is at team is on team 1 and 5 is at team 2. Okay. So this is one arrangement, and the output is similar to here only. Cool. Now let's think of the case where this arrangement is not possible. Okay. Let's say I have an arrangement something like this. Okay. Now, when I have an arrangement like this, if I start with 1, if I assign it to team 1, then I have to assign 2 and 3 to different teams, that is team 2. Okay. But if we now look at 2 and 3, they are now in the same team, but I have a friendship in between them. So this is like contradicting with the problem statement, right? So whenever I have this kind of arrangement or this kind of connected components, then uh, division of pupil into team 1s and 2 is not possible. Okay. So this is the case, like this is the case where we have to output impossible. Okay. And if I do not have this kind of cases, I can simply print any arrangement, or I can do any arrangement. So this is a standard problem. We call it black and white color mapping. Okay. Now this standard problem states that whenever you have a node, so it's certainly like you have a graph, and for let's use black. Okay. So for each node you have to decide a color, and the condition we have to follow is like we have to color one node black and all of its neighbor to white. Okay. So this problem is pretty similar to what we have here. Here, instead of coloring, they have used the term dividing into teams. Okay. Now you can like look for GFG or any article. So this is the general problem statement we have. Okay. Now the question comes like how we solve this. Okay. So solving is pretty easy. So we can use a DFS or a BFS kind of algorithm. Okay. Now, whenever I am at a node, okay, let's say the color of the node is some C, okay. If its adjacent nodes are not colored, okay, then I have to put a complementary color, okay. But if one of the node is colored already, Okay, I have to check whether that node is a complementary color or the color to which like this parent node. Okay, if the color of the parent node and color of this node are same, okay, then we are contradicting. Okay, then we cannot proceed, so we can directly output impossible. Okay, but if it is not assigned, we can assign a complementary color, and if it is assigned and it's already a complementary color, then we are good. Okay, so this will be the implementation. So whenever I'm at a node in BFS or DFS, so for all of its neighboring nodes, okay, I'll be using a complementary color. Say graph of node. Okay, so I'll be assigning color. So, and yeah, before that I will be checking if n node is not colored, or as per this problem statement I can say if n node is not assigned to any team. Okay, then I can put like team of n node as complementary. So here for complementary I can use like 3 minus team of node. Why 3? Because let's say uh, team of node is 1. Okay, then what should be the complementary of 1? That is 2, right? So I can directly get 3 minus 1, that is 2. Okay, now let's say team of my node is 2. Okay, now for 2 the complementary should be 1, so I can do 3 minus 2. Okay, so which is 1. So that's why 3 here. Okay, so just to put the complementary team here. Okay, now this is the case when n node is not assigned to any team. Okay, another condition is if n node is assigned. Okay, then I have to check if n node or team of n node is complementary, is equal to 3 minus team of node. Okay, if this is the case, then good. Okay, we can proceed to other nodes, we can continue. Else, if it is same as the team of my of its parent node, which is this node here, then I can print impossible. Cool. I cannot proceed because these two are like same. Okay, so I cannot do any team arrangement more. I can simply break out of the DFS or a BFS. Cool. Now let's jump to coding. Okay, so we have been given number of nodes and the number of edges, that is n and m. Let's quickly take that. Okay, then let's build our adjacency list. Graph of n plus 1. Okay, n plus 1 being because all the nodes are given in 1 base indexing, so why to do that 0 base indexing transformation by doing minus minus on the nodes. Okay, now the number of edges, a b, then graph of a, I'll be pushing b, then graph of b, I'll pushing a. Okay, now let's build a mapper for the teams. Okay, so team mapper, let's say. Okay, and let's put initially none of them are assigned. Okay, so let's code a BFS solution. Okay, you can do the same with the DFS. I'm just coding it in BFS just to keep all the functions and intact within solve. Okay, so push, and yeah. Okay, now in this problem statement, if you look at here, so all the nodes are not connected. Okay, So we have to do a multi-source BFS or a DFS. Okay. So we will be having a for loop that will iterate over all the nodes that we have. Okay. So let's say I 1 to I equal to n. Okay. Then I will be running a BFS on this if only the color of this node is not assigned, or the this node has not been assigned to any team. So if team mapper of I is -1, let's say if it is not -1, like let's say it is assigned to a team, then I don't need to proceed for BFS. If it is not, then I have to put it inside my queue. So queue dot push I, okay, and then I will be running my BFS while queue is not empty. Now let's collect the node queue of front, then queue dot pop. Okay, now I'll be traversing its neighboring nodes. So for auto neighbor node of graph of node. Okay, now if neighbor node is not assigned to any team, okay, if it is not assigned, then I can do for my neighbor node, I can put it in, I put it inside a complementary team, which is 3 minus t mapper of my parent, like my parent node. Okay, and I can put this node inside my queue for further processing. Okay, but if it is assigned to a team, okay, else if team mapper of n node, if it is already assigned but it is uh same as, okay, it is same as my parent nodes team, okay, then we cannot do anything. So I can simply put a impossible and I can break out the function, like directly return from here. Okay, cool. Now if this condition is not happening, then we will be assigning every node to one of the teams. Okay, and in the end we can print out the result. So for 1 to n plus cout team mapper of I, and this should be space separated. Cool. Now let's run this. I have already taken this input here. Let's run this. Cool. We are getting something different here. Oh, because whenever I'm putting inside the queue, I should assign a team. So team mapper of I, let's start with 1. Then as we are spreading to its neighboring nodes, we will be putting them into a complementary team. Cool. So yeah, same as here, 1 2 2 1 2. Now let's submit this. %, 17%, 92, and ready. Okay, all got accepted. Now let's quickly do a time complexity analysis. So taking the input, so whatever edges we are getting, we are putting this inside our adjacency list. So I will not consider that as I will not consider this in the time complexity analysis. Let's look at here. So we are doing a multi-source BFS, but even if we are doing a multi-source BFS, so we are only running this for only those nodes which have not been assigned to any team. Correct. So it basically means we are not doing any nested iterations. So the number of nodes and edges that we have, we are only traversing that. So the time complexity will be big O of n plus e. Correct, because I'm only doing the BFS only when this is not assigned, right? and the BFS will make sure that whatever nodes are connected to this node are also traversed. Okay, so I will not be revisiting those nodes again and again. Cool. Then yeah, in the end I'm just like printing the answer, so that's again a linear uh, operation. So yeah, at worst time complexity, my BFS algorithm will dominate over this linear printing. So yeah, this will be the time complexity. Then for space complexity, so yeah, again taking the input, putting them inside the adjacency list. So this is depending on the input, the edges that I have. So let's not consider this in the space complexity. Now here I'm using a team mapper data structure for building a mapping between the teams and the nodes. So it has a size of n. So as my number of nodes increases, this will increase linearly. So a big of n. Then we have Q. Now Q will be storing at max all the nodes inside it. So it's again big O of n, like the number of nodes. Then yeah, then we are not using any other data structure. So this is all the consumption. So the overall space complexity will be linear. Cool. So yeah, so this is how you can solve this problem, and feel free to do it in the DFS approach. DFS is also pretty easy. And yeah, so I hope you learned something new, and just stay tuned to watch more videos.